Okay. Questions? Yes.
Can you like do the I don't know where this better, but like the big ideas from chapter 5 with the quick action stuff, like stuff that we like really need to know. I don't know. I'm confused on chapter 5. I was reading through it and it's like I don't know how.
What is chapter 5?
Chapter 5 is the group actions.
Okay, and so what's the question on that?
Like could you just go over like I think what would be helpful is like the main ideas of it, like
So the idea of a group action is you have some set. But it's not empty. And G is a group. So an action is just a function from G cross S to S. And this is written as little g acts on S, GS. So it's just a way of pushing things around it. That's all it is. One of our big theorems is there's a one-to-one correspondence between actions of a group on a set and homomorphisms for that group into the permutations of that set. So basically what you're doing is you're just rearranging elements of the set. And that's all there is to it, really.
okay, so you're just like you're saying like oh this is acting on it, it's the same set, you're just moving stuff around.
That's exactly right. And what's often done is G acts on itself. And a couple of common ways that might act is so if you have so G is now acting on the set G itself. And the action, G action on X, just gives you the ordinary multiplication. All right. And actually, believe it or not, sometimes this reveals things about the group. G might act on itself by conjugation. This is useful too. And an action, there's only two things that an action has to satisfy. Well, let me put this. Yeah, number one, the identity of G acting on S. So whatever the set is being acted on, the identity leaves everything alone. That's it. And number two, so it does something like associativity. And those are the rules that it must follow. We proved actually classes both of these rules, both this defined action and this defined action satisfy both. And really, actions were used as tools in other things, like proving Sylow theorems, It's very common to do things like, in some of these applied problems where you're trying to figure out if there could be a group that's simple of order, whatever it is, 56, then oftentimes you look at G can act on the Sylow. So that's another set. This is G act on. But the group of transformations for Rubik's Cube, that acts on the Rubik's Cube itself, just by whatever you do with your hands, that's an element of G. And it satisfies those two rules. The identity, you don't change the cube. Example. G ring. And we'll say it's finite. And to K. So you have the Sylow P subgroups. We'll call the set S. Then P acts on S by conjugation. So G acting on PI, G, PI, G. So it just pushes this to perhaps a different Sylow P subgroup. We know all the Sylow P subgroups are conjugate, so this is what we call a transfer action. Because given any two of these, there's something in G that takes it to something else. And this is an action because if you have E acting on PI, this is E, PI, E inverse, which is PI. So the identity left alone. And number two, if you have G1, G2 acting on PI, this is G1, G2, PI, G1, G2 inverse. Right? Now I can turn this around. Right. And if I think of it this way, this is G1 acting on G2, PI, G2 inverse. Right? That's exactly what that is. And this inside the parentheses is G2 acting on PI. And so I got exactly what I was thinking.
So for that example, you were able to, like, you knew it was conjugation because it's the Sylow subgroups. Okay.
Yeah, that's right. Left multiplication doesn't work on this set because when I take E1, say, and hit it on the left by something in G, that's no longer a Sylow subgroup, so it's not the setting.
Okay.
Yes.
Can you do 4B from the fall 2025 exam?
Fall 2025. This is show that if the order of G is 24, that you can't set it.
Yes.
Okay. Well, this will, I think, yeah, this will be a group action. So the instructions here are show. You have order key on 4, and by the way, it's 2 cubed 3. Then G is not set. Okay, so first thing is I will throw the Sylow theorems at this. And let's see. The only problems that divide 24 are 2 and 3, right? So if I'm looking for Sylow subgroups, there should be a Sylow 2 subgroup, right? And that should have, what should the order of the Sylow 2 subgroup be? How many elements in this?
Is it 3? It's the order 24 divided by 2.
No, I think, I'm not asking how many Sylow 2 subgroups are. I'm asking, when I have a Sylow 2 group, how many elements are in it? 8, right? So the Sylow 2 group actually has 2 cubed elements in it. So the Sylow 2 group, and there's at least one of them will have 8 elements. The Sylow 3 group will have just 3 elements, right? So they might be a little bit easier to handle. The number of Sylow 2 groups, I think this might have been what you're getting at, is equivalent to 1 mod 2, which just means it's odd. And in fact, it must divide 3. So I don't know how many there are. I just know that there's 1 or 3 of these. Agreed? Yes.
So can you just explain again what the 8 means? The number of elements inside each.
When you have a Sylow 2 group, it will have 8 elements in it.
Oh,
So the group, the Sylow 2 group itself is of size 8.
can you explain where that comes from?
2 cubed.
Like, which, like theorem or something?
The Sylow theorems. And the definition of the Sylow subgroup.
Okay.
A Sylow subgroup is then the elements. Yes.
You know which is the best path like N2 or N3 because when I tried the problem I did N3 and I couldn't get an answer. But
So what did you try?
like I tried to find N3 and it was a lot harder. So I didn't know like
Oh, okay. Okay. We'll get to that. Yeah. So this we've got 1 or 3. Agreed so far. So the divisors of 8 are 1, 2, 4, and 8, right? Which of those are equivalent to 1 mod 3?
1 and 4.
1 and Now, one trick that we used to use with Sylow theorems, and in fact, I think this trick actually does work in part A, but it doesn't work so well here. If G is simple, but we're going to assume G is simple and kind of go for a contradiction. If G is simple, what are the values? Right, they have to be 3 and 4. Because the number of Sylow peak subgroups is equal to 1, game over, because that thing's normal. Right? Everybody okay with that? And now, did you try to count elements? This is right. This one doesn't, this one works. The counting elements method, I think, is effective on the previous one, but not so much this one. And here's the problem. Counting elements in the 4 Sylow 3 groups is easy because you've got 4 Sylow 3 groups right? There's no overlap between any two, three group other than the identity, right? Because they're all cyclic prime order, right? So if you've got 4 three groups, every one of those 3 groups has 2 elements of order 3, right? That counts for 2 times 4 is 8 elements of order 3. That leaves you 16 elements, but that's more than the 8 you've got left over. And that's probably where you ran into a roadblock, right? Because it's like, there's not enough to count. You also don't know, and it is true that, okay, maybe I've got 3 Sylow 2 groups, but you don't know how they intersect, right? If they intersect trivially, like only in the identity, then you can probably count things out. But they could intersect in the subgroup of order 4, and now it's much more complicated to count things. You might could do it, but here's a shorter way. I'm going to focus on 3 just because it's small. It doesn't matter. I can make this. I could make this plain fly with either one of these. So consider as I'm going to call this P1, P2, P3. The 3 Sylow subgroups. Everybody okay with it? And I'm going to let G act on S by conjugation. Just like we did before, right? Any element of G acting on one of these PIs is GPI, G inverse. And what's the big theorem that we had about group actions? And that is there is a homomorphism from when you have a group on the set. This gives you a homomorphism from the group to the permutations on the set. So this gives G into permutations class. Right. That actually gives rise to a homomorphism, the G into the permutations class. And that's all you really need to know, because if somebody tell me what are all the permutations best, what's the different permutations on a set of 3 things? Yes.
Is it S3?
It's S3. So we have some V, it goes from G into S. I agree with that. And that's the heavy lifting part of our group actions get the homomorphism. Now, let's think about this for a moment. How many elements are there in G? 24. How many elements are there in S3? 6. So the first thing that I realized here is there's no way on this God's green earth that P is 1-to-1, right? Right? There's no way this is 1-to-1. Because G is too big, right? Or the size of G, I should say, is too big. I agree with that. So the kernel of phi is not the identity. Because if the kernel of phi were the identity, it would be 1-to-1. And also, there's one more thing. The kernel of P can't be all of G either. Anybody tell me why? This is a little subtle, but it's not too bad. Remember, G acts on if the kernel is all of G, that means every element of G is the identity permutation. That means whenever you conjugate any one of these, it leaves it alone. Everybody heard that? That means they're all normal. And that can't be because there's multiple. Another part of the Sylow theorems is all the different Sylow P subgroups are conjugate. Remember that? So you have to be able to conjugate this to this. But if it's all fixed, you can never go anywhere, right? So there's two ways you can think about that. A, that means that all three of these have to be normal, which is ridiculous because there's three of them. Or it also contradicts the Sylow theorems because they all have to be conjugate. So the kernel can't be all of G, because if it was, it means the action's trivial and there's no movement at all. Do I agree with that? What's the significance now? Yes.
I was gonna say that the kernel's always normal.
Correct. And the kernel P is not G, and it's not the identity. So that means that G is not simple. So there's no simple group of 24. Yes.
When you're doing that, do you have to prove that there are three groups? Or do you just do case by case if there's one group and that group's with itself?
Well, you got to know the number. I mean, this was key right here. The Sylow theorems tell me what the possibilities are. If either one of these possibilities was one, we'd be done, because that would mean if this were if N2 was one, that would mean that the Sylow 2 group was going more different. So you have to have this case right here, right? So you know that N2 there has to be three Sylow.
Or couldn't you just say if there's more than one, then one P must go to another P and use that to prove that the kernel can't be all of G?
Yeah, but then you've got an entirely different situation, because what was key in this was the fact that this was S3. That's how you knew the kernel couldn't be one. But S3 keyed on the fact that there were exactly three Sylow P subgroups. Yes.
So if our subgroups are like not one right away, should that be our first instinct to do that we just did instead of counting elements?
Well, let's do the previous one actually, and I'll so yeah. Let me do the previous one. That might illustrate this. Yes.
Can you go over what's on this for again, like where, how does G, I don't understand the part where it's like G goes to the permutation of S and S. I like it.
Do you understand this part? Just this right here.
Yeah.
This is a theorem from the notes. This is
Okay.
a theorem that we proved that said there's a one-to-one correspondence between the actions of G on the set and homomorphisms from G into S permutations of the set.
Okay,
And so this action here gives you a homomorphism permutation of S. And the reason this is isomorphic S3 is because there's three things in the set.
okay,
Right.
oh, okay, yes.
Is that clear up? Yes.
Yeah. Okay, yeah, so then this, so are you using that for to get a contradiction? Right?
I'm using this to get the fact that there is a homomorphism from G to S3.
Okay,
This group has 24 elements. This group has 6 elements.
right, so that can't be one to one.
So it can't be one-to-one. So I know that the kernel of this map, the kernel is going to be normal, right? So if this is simple, the kernel has to be either the identity or all of the group.
Yeah,
If it's the identity, that's impossible because it's too little.
Yeah.
Right, and if it's all the group, that means that the action is trivial, which the Sylow theorem tell us it's not,
Yeah, yeah,
right? And so, yeah, that's how this argument always kind of works.
yeah, okay.
Right? But Julia, you were asking about, how do you tell? Well, I try to count elements if I can. If it appears that it's easy. Let me do the previous one, and I'll leave this case up here. Contrast. So suppose. G, well, I'm gonna go through kind of the same sort of stuff. Uh, oh, one or eight. Wow. Now, so I'll kind of structure this a little different, just for show you a way of thinking. Uh, like if into one, then e not so. Right? That's right out of the gates, because there's only one set of roots. So let's assume it's 7. Uh, oh, I'm counting. I'm lost my mind here. Let's see. And 7 as well. So let's start to something. If in 7 you can form, then you can see. I'm keying on the 7 group for the following reason. It's easier to count things there because 7 appears only to the first power. This power here, the Sylow 2 subgroups report 8. This makes counting things difficult in a way that I would rather not deal with. So if N7 is 1, out of the gate, V is 7. Good. So suppose N7 is equal to 8. Right? Now, let me point out that any two Sylow 7 groups are cyclic of prime order. So their intersection, if they're different, can only be the identity. Everybody agree? So if there's 8 of them, this accounts for 8 times 7 minus 1, which is 48 elements in G 7. Right? Because every one of those Sylow 7 groups has the identity and then 6 elements of order 7. So if there's 8 of them, that gives you 48 elements of order 7 floating around in G. How many elements does this leave? There's only 8 elements left over. So there's only room for one Sylow 2 subgroup. Right? And there you go. So what we've proven is either N1 is 7 or N2 is, I'm sorry, either N7 is 1 or N2 is forced to be 1. So no matter how you cut this cake, you've got a normal Sylow subgroup. And so it's not.
You don't have to add the identity back in.
Oh, because I only counted elements of order 7 here. So, and what's left over, the identity is one of them. Right? So the identity is one of these 8 left over. Because here's the 56 elements, and I took all these elements I've taken away, all have order 7. So everything left over will include the identity. Yes.
So I do this example, is there something that so
Yes, because we had exactly enough left over in this one for one Sylow 2 group, right? And the other example, when we counted, we had 16 elements left over, and the Sylow 2 subgroups were size 8. So now it's complicated. How are they intersecting? Okay, was that clear? Do y'all understand what we did there? Okay, good. What else we got? Yes. Oh, the elementary divisor and very, okay, let's do that. Let's do one of those. Yeah, I want you all to feel comfortable with things because I almost guarantee there'll be something like that. And so clean up. Okay, so let me make up some stuff here. I'll do a couple of problems. Number one. Inspiration to only do that. Yes. How many abelian groups were 1,600 are there? And be glad that I said abelian because I'm quite sure that I said that would be thousands. First thing I want to do is I want to factor 620, which I think you better check me into this. Yes, 20 to take the one. Okay, so I'm going to find all groups of order 1620 in both elementary divisor and invariant factor decomposition. Okay, so maybe the first thing to do is help us out. How many groups? Let's break this up by prime powers. How many groups of order 4 are there that are abelian? Actually, all groups of order 4 are good. Well, you can break this up this way. 2 squared, or, well, actually think about partitioning this 2. 2 is 2, and 2 is 1 plus 1. this corresponds to C4, which is 2 squared, or C2 direct sums. There are actually 2 groups of order, C4 and C2. Everybody okay? How many groups of order 3 to the 4 are there? Abelian. Yes,
So is it always true that the number of groups is equal to the number of the exponent?
it's partitions in the exponent. So here what we're doing is partitioning 4. How many ways can we partition 4? 4 itself. 3 plus 1. 2 plus 2. There's only one way to partition it, one number. There's 2 ways to break it down into 2. One way to break it down into 3, I think. That's the only way to break it down into 2, but 3 bits. And one way to break it down. So this is C4. This is C3. Sorry, C81. C27 direct sum C3. C9 direct sum C9. C9 direct sum C3. Direct sum C3. And finally, 4 copies. These are all the different isomorphism classes groups that you want. Cyclic order 81. I can bring it down to cyclic 27, cyclic 3, 2 cyclic 9s, cyclic 9, 3, 3, and also. Everybody okay with that? Notice this gets more complicated because basically the number of different groups to address that question, it's the number of ways that you could take the integer that's the exponent and break it down into sums of smaller things at least one. Yes.
And we use addition for the set of integers.
Where am I using addition?
When we partition the exponent.
Yeah, think of this as addition. These are basically the pieces parts. This is 3 to the 4th power. This is 3 cubed direct sum 3 to 1. 3 squared sum 3 squared. And those partitions, those give you the ways to work them. And order 5, that's easy. And that's it. So somebody tell me how many groups of order abelian groups of order 1600. So what I mean, I'm gonna write on that. What's my grand total? How many different groups of order 1620 that are abelian? I'm not gonna have it.
The 8.
No.
Are you not just counting?
Remember, to make it a group for 1620, I've got to stick these all together. Right? So these are, think of this list as the possibility of Sylow. These are the possibilities of the Sylow 2 group. It can look like this or this. This is the possibility for the Sylow 3 group. It can look 5 different.
10.
That is correct. It is 10. So you're making a choice every time. Pick one, and pick one, but you know what you're going to pick here. All right. So I'll make the list via the elementary divisors. So I will do this. elementary divisor, invariant factor. Okay, I'll pick C4, C81, C5. That's the elementary divisor decomposition because I've got the prime powers kind of stuff together. What's the invariant factor decomposition? We'll see what this one is. Remember, y'all remember you can put these back together if they're relatively prime. So you group this as a Z324, and you can group this times this. This is actually the second one. Second choice. I'll leave this as Z4. But my second choice, I will go C27, correct sum C3, correct sum C5. So the only thing I've changed there is the Sylow 3 group. It looks a little different. Geez, y'all know what this one is? Do a greedy algorithm. Stick the biggest together. 4 times 27 times 5 is 540. And I'm left with C. Here's the invariant factors, 3 and 5. Yes.
Doing that because 427 and 5 are relative prime, but 3 isn't relative. So,
That's right. So I do a greedy algorithm. I pick these out one at a time, right? Biggest, 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 and then second biggest, second biggest, second biggest, and so forth, right? But of course, the next step, I'll run out of stuff here and here, and that leaves me on the C3. Next one, and you'll see a difference in a couple. This gives me C3, no, I'm sorry, C180. Correct, so. Keep moving down the list. The next thing on my list is again, I'm gonna get 180. But I'm trailing this time the C3 and the C. And finally, here I'm going to get a 60. That's when you three. There's half of it. Now I've exhausted all the possibilities for what can happen with the Sylow 2 group being Z4. So now I'm going to move on this and exhaust the possibilities. Z2, some Z2. sum C81, sum C5. Or it should be C what? Yes.
Is it 8?
Was that 18? Okay, next, I get C2, sum C2. Sum C27, sum C3, sum C5. Okay, be greedy again. 2 times 27 times 5 is 270. Now I've eliminated the top choices. C2, C3, and C6. People. C2, C2, right, so C9, C9, C. I'm sorry, C5. This will be C90, C8. Only a couple more to go. C2, some C2, C9, some C3, some C3, some C5. Now I want to get 90. Next one down with 6. And the next one. I'm sorry. That's C5. No, I'm right. C90, C6, C4. And finally, C2, some C2, 4 C3s, some C5. Well, C30. So that takes care of that, that, and that. C6. That takes care of that and that. And the only thing left are 2 C3s. So there's a complete list of all the abelian groups for 16 through 20, all 10 of them, in elementary divisor form on the left and invariant factor form. Any questions? Yes.
And get to 12.5, you start out with something in the form of a direct product. It's not in its own applies with decomposition and mass. So they've done to see those.
All right, I'll go through that one. I was actually going to do one of those next. This one, number 3, you're looking at on the previous thing.
Yeah.
C96, C144, yeah, we'll do that one. So what if I start off with some? So I just asked you to find all the groups for 1620, which we did, abelian groups for 1620. What if, so I'm giving a specific group and the problems being discussed now. The specific group is uh, 96, 144. Z45 and Z6. Now, the first thing that I do. Yeah, so this is a two-part problem. I'll kind of do them both in tandem. Find the elementary divisor decomposition, find the invariant factor decomposition. I'll pull this apart at the elementary divisor first. G is isomorphic. What I'm going to do is I'm going to factor these into prime powers. 96 is, I guess 32 times 3. 144 is, I guess, 12 squared, so that should be 9 times 16. 45 is 9 times 5. And 60 is 2 squared times 3 times 5. So those were all, so I factored 96, 144, 45, and 60 in prime powers. So I can pull apart C96 is C32, direct sum C3. I can put that together and pull apart too. C144, C16, direct sum C9. 45 is C9, direct sum C5. And 60 is C4, direct sum C3, direct sum C5. Okay, first step. Do you all see how I got that? Right. And in fact, in a certain sense, you can argue that this is already an elementary divisor form because I've got C prime powers, everyone's prime powers, but it's messy. And I'm going to put it in a better form here. So I'm going to put this in elementary divisor form. It's isomorphic. I'm going to group this by primes. See, prime powers, I can essentially say. This is C32. Direct sum 16. Also, direct sum C4. Okay, so that's all the twos. That looks good. Three's the next part out. Shows up. Looks like I got 2 9s and 2 3s. And I guess the only problem I've got left is 5, and I just get some C5s. Let's see, 2, 4, 6, 9, 3, 7. So all I did in this step is I just regrouped it and put the prime powers together in descending order. So this is the elementary divisor decomposition. Notice that first block in parentheses, C32, direct sum C16, direct sum C4. That's the Sylow 2 subgroup. The next one, the 2 Z9s and the 2 Z3s stuck together. That's the Sylow 3 group, and the Z5 is the C5. Okay. There's your elementary divisors. I also asked for invariant factor decomposition. So I'm going to do just what I did before. Take these apart. So we'll see if I can have it. Like this. 32, 160, 69, 1.7. So 32, 5 to 160 times 9, so a 4 off goes off. And I got C from Q. By the way, I don't give a right. C sub 2 to the 5th times 3 squared times 5. That's okay. I'm pretty sure you can tell that. Please don't try to prove me wrong. Next. All right. So it's just a greedy out going down. 16 times 5 times 9, so that's 20. Everybody okay with that? Okay, then pull the next one off. We're out of fives at this point, so it's going to be a C4, C3, C12. And finally, this is by the way, of course, the number of invariant factors that you have should equal the length that belongs to one of these, which is 4. Right? Think about the way the algorithm works. And these are invariant factors. Notice 3 divides 2, 3 divides 12, 12 divides 7, 20, 7, 25. Everybody okay with that? Yes.
When we're doing this in the exam, can we kind of just do it like that, or do we need to write in like theorems and definitions?
No. Yeah, so you got to criticize on the homework. That's what you're working on, right? You get a lot more latitude on the exam. I will if you're not very right. I mean, don't just write a bunch of gibberish. I mean, say these are the invariant factors. Say something in a roadmap, but no, you don't need to chapter and verse things. Yes.
Invariant factor is the invariant factor composition.
Yes. Yeah. Given the so it determines the group uniquely. And in fact, the invariant factor is this the largest invariant factor. This one is 1440. That's the exponent of the group. So notice the order of the group is, I'm not going to multiply it out, but it's the product of these 4 things, right? So the order of every element of the group divides that order. But in fact, the order of every element of the group divides 1440. That's the exponent of the group. 1440. There's an element of order 1440, and every element in that group has order dividing.
So using the Greek algorithm, stuff is required. Right? Or is it just so ends up that if you fix things randomly,
Oh no. If you pick them out of order, you're not going to get you might. So what has to happen? The reason we do this greedy is I do it sort of backwards from some way some people do it, but I go big to small because then it's more clear for what kind of stuff. I think. But anyway, you have to pick it big to small because what you want is you want this guy to divide this guy to divide this to divide this, and so forth. And if you don't do that, if you don't pick it in decreasing order, you might screw up that division.
Okay.
Okay. Other questions? Or do y'all feel like if I threw this down in front of you now, you kind of do it, work it out, right? And actually, you asked the question, so was that okay for you? Okay. Yes.
So one of the questions from the exam to the fall was like it's write the element of S6 to 5, the big one thing is product of different cycles. And then the next part is to write it as a product of transition.
This is like 1A. Right.
Yeah, it's 1A.
Okay, so it's gonna be useful for me to work all the way through this whole thing. Actually, why don't you guys see if you can work through this? I want to make sure that you all are good with this. We had something like this on the last exam too, didn't I? Because I introduced this stuff with you.
So we had the disjoint cycles part. It's just with transpositions and all.
2, 5, 3. You could write this right out of the gate as a part of disjoint transpositions. It's better to wait until we're done with part A. One, 3, 5, 2, 4, 5. Three ones. Okay. You guys take me to see this. I'll get you. Race. Somebody tell me when you're done.
He does it.
Yes.
I said.
Oh, you got it? Okay. Well, I'll start with one. Where does one go?
Sorry, you're gonna go. So I got, one goes to 2, then 4, 3, 5, 6 is on its own, like, if that's wrong, so I expect that 6 goes to something else.
Okay. Anybody else?
Does that one go to 6?
What's that? Oh. Min said maybe incorrect, so. Yeah, I agree.
Okay.
Okay, so one goes to, let's go through this. One goes to 6. Nothing, nothing. 5 to 6, nothing, nothing, nothing. So it ended up, right? How about 6? Went to 5, 2, 6, 1, 3, 2. Anybody can get what I'm getting, yell at me. How about 2? 2 goes to 4. 3, 2, 5, 4. Agree? 4 goes where? 4 goes 5, 1, 2, 3, 1, 3. Agree? 3 goes to 1, back to 3, 1, 5, 3, 5. 5 goes to 3, 5, 4. Close enough. So, has everybody got what I got so far? Yes. All right, here. 1, 2, 3, 4, 5, 6. And that's it, isn't it? If I used up all that, okay, so let's go next one. Everybody got that, right? Here is. This is equal. Write any cycle as a product of transpositions. One thing that you can do, there's many ways to do it. One thing you can do is just fix A1. Notice A1 is always first here in these transpositions, and then go in reverse order for the others. Right? And let me show you why this works. Where does A1 go? A1 goes to A2, and there's no more A2s. So it did what it's supposed to do. Where does A2 go? Goes to A1 to A3, and there's no more A3s. So A2 goes there. Where does A3 go? Goes to A1 to A4, and then there's no more A4s. Blah, blah, blah. Where does AN minus 1 go? Right, AN minus 1. There aren't any AN minus 1s until right here. Well, let's do AN minus 2. Where does that go? There aren't any AN minus 2 until right here. It goes to A1 to AN minus 1. AN minus 1 goes to A1 to AN. And AN goes back to A. Which is exactly what's supposed to happen. So, if you want to write this as part of disjoint transpositions, one, 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 one. 5, 3, 4. 6. There you go. Yes,
You talk about part C on that exam?
part C.
Yeah, one C.
For what value's been greater than or equal to 3 is AN simple. Everything except 4. Right? It's simple for n equals 3 because A3 is actually cyclic of order 3, right? And that's always simple. Prime order groups are simple, right? And the rest is a theorem from class that AN is simple for n greater than or equal to 5.
What is?
I don't know what the number is, but it's, I promise you, it's in the part where we talk about symmetric groups. I threw 3 in because 3 is easier in the following sense. A3 is a order 3. So it's cyclic, prime order. So it's simple. Right? Yeah, but beyond that, A4 is really, A4 is a weirdo because it's not a cell, but at 5, yeah. Okay, other questions? I know you had to go some, did you get all your questions done now?
Are you?
I'm sorry?
Are you recording?
I am,
Okay.
yes.
So for something to be a zero-divisor, it has to be a left divisor.
Right, but you don't have to use the same element.
You're asking my question, it has to be the same.
No, it doesn't, right? So if Bill hits it on the left, it makes it zero, and Fred hits it on the right, makes it zero, it's a zero divisor. Yes.
Can we actually do a question like that where it's like a zero divisor
I'm sorry, zero divisor what?
and nilpotent? And
Oh, you want to count? Yeah,
Yeah.
okay, yeah. Well, that's hard. Give me a number. A positive energy. And make it fun. No unfun. Just fun.
73.
Okay. You don't happen to be a fan of Sheldon Cooper, do you?
I actually just saw that clip on Instagram on my
Is it?
reels. Yeah, that's why I picked it.
One of my former PhD students in that episode or a later episode, one of the props they use on those paper, one of my former PhD students, where he and his other number theorists actually proved a lot of the things he said about the number 73 in that episode.
Really?
So that's his plain fact, which is kind of cool. Okay, so what happens for 73? And then we'll do another one. Okay, so I want to find zero divisors, units, nilpotents. Let's start with the units. How many units are there in Z73? There's 72. Well, Z-mod 73 is a field. Suppose n is an integer, positive integer, somewhere nestled between 1 and 72. What can you say about n, the greatest common divisor of 73 in that n? It's 1. Do I agree with that? Okay, so let's go back to the old class. The greatest common divisor of this n, 73, is 1. So there exists such that nx plus 73y is equal to 1. Right? Because the greatest common divisor is a linear combination of n and 70. Reduce this mod 73, and this means nx is equivalent to 1 mod 73. So whatever this n is, x is its inverse, wherever that x happens. That means that in Z73, every one of these numbers between 1 and 72 is a unit. They all have a multiplicative inverse. So it's a field. So there's 72 units, basically everything's 0. There's 1 nilpotent, it's 0. 1 zero divisor, it's 0. Yes,
Can you explain a little bit more on how you got those?
got what?
The zero divisors, units, and nilpotents?
Well, because this is a finite ring, right? Everybody okay? You okay with that? And in a finite ring, one of the theorems we proved is every element is either a unit or a zero divisor.
Yeah.
We know that 1 through 72 are all units, right?
How do we know that they're units?
because I just constructed the inverse.
Right. Okay.
M times X is 1 minus 73. So if it is any one of these numbers, whatever its X happens to be, is its inverse, right? So all those guys are units. That leaves only 0. And I know for a fact 0 is both a unit and I'm sorry, it's both a nilpotent and a zero-divisor. All right, so that's how I got that. Let's do something a little bit more exotic. How about this? Uh, let's look at C. Now, let me, before I get started, so here's the problem. I'm going to ask in C18, I want to count, and not just count, I want to also list zero-divisors, units, and elements, right? So, you all may not remember this. We talked about the Euler phi function earlier in the notes. Basically, what the Euler phi function does is it counts the numbers between 1 and whatever this n is that are relatively prime, right? There's GCP on. And the Euler phi function works on the prime powers like this. Phi of 2 is 1, and this is 2, phi of 3, and phi of any prime is 12. Or phi of prime power is that's fine. So that would be 3 equals 1 times 3 minus 1. So that's 6. So I predict that there are 18 things. We've 1 and 18 that are relatively prime. I guess I'll toss those. Forgive me for not putting the bars on them, but these are my elements of C. Think of these as integers. Which ones are relatively prime to 18? Well, this one, this one, this one, this one, and of course, 2, 4, 6, 2. This is what's supposed to be. These ones all turn out to be prime, which is a coincidence. Well, they don't all turn out to be prime. One is not a prime, but the other ones are. Okay, so the units. There's 6 of them. Agreed. Okay. Everything left has to be a zero-divisor, right? Because this isn't true in general, but it's true here because it's a finite thing. So what's left over? The zero-divisors. Are 0, 2, 3, 4, 6, 8, 9, 10, 12, 14, 15, 16. Now, nilpotents should be a subset of this. The only one I know for sure is zero will be a nilpotent. There may or may not be others. Are there others? There are.
It's there.
Okay, you're on the right track here. Here's the problem though. To be a nilpotent, if you think of it this way, when you jack it up enough with a big enough power, it's got to be zero. Right? Another way to put that is if you make it a big enough power, it's got to be a multiple of 18, right? If you take 3 by itself and look at powers of 3, you're never going to be a multiple of 18, right? Because even though you've got as many 3s in there as you want, you never have that 2 for it to be a multiple of 18, right? So you need stuff with both a 2 and a 3, right? Anything, if a big enough power is divisible by 18, it had to have had a 2 in it and a 3 in it, right? And that's enough. Those are your 3 nilpotents. Notice that they actually formed an ideal of this ring, right? Because if you they're actually an ideal. The nilpotents actually do form an ideal. They're closed under addition and multiplication from in the ring. Right. Do the zero divisors form an ideal? The nilpotents do, but what about the zero divisors themselves? Yes.
Can you explain what you mean by the nilpotents form an ideal array?
That's a theorem we actually proved in homework, right? If you have a commutative ring with identity, well, commutative ring, which we certainly have here, right? C18 is commutative ring with identity. Then the nilpotents are closed under addition and multiplication from elements, right? So they actually form an ideal.
But closed under addition and multiplication just means it's a subring, not.
Multiplication from elements in the ring. Right?
Oh,
So
oh.
notice if you multiply, so the nilpotents are multiples of 6, so right? And if you multiply anything in that ring by multiple 6, it'll still be a multiple of 6, it'll still be nilpotent. Right? If you multiply, say, 6 by 7, that's 42, which is again 6, right? Mod 18, right? Because subtract 18 equals 6, right? So if you multiply 0, 6, 12 by anything in that ring, you will get either 0, 6, or 12. It is an ideal.
So in that case, like 6 is like the I, 7 is like the R. And we're multiplying.
In the example I gave, 7 was like the R, and 6 was like the element of I.
Oh.
Yeah. How about the zero divisors? So they form an ideal? So, they do not. What's the problem with the zero divisors? Ideals have to be subgroups too, right? They have to be closed under addition. Nilpotents, yes. Zero divisors, not always. And in this case, I said, what's 3 plus 4? 7, right? Is that one of the zero divisors? No. So the zero divisors could form an action. Yes.
Sounds why we have to do all this for 8 to 8
Because 73 is prime and 18 is more exotic. I mean, we did do all this for 73, but there wasn't much to do because in the first step, we figured out that everything that wasn't 0 was a unit. So we were kind of done there. It's more complicated here. Yes.
Can you go over the zero divisor part again? Like, I don't understand how I understand how we have units, then how do we know what is?
It's everything left over.
Is that always the case?
Only in a finite ring.
And you're saying a finite ring would be like C mod, whatever.
Any ring that only has finitely many things in it.
Okay,
And this is one of them because it's only got 18 things in it.
Okay.
So when you jerk out the units, everything left over is zero divisor.
Okay.
Yes.
So if it's not a finite ring, then it's that element, or it's the power of that.
Well, I'll give you, here's a good example of this. The integers is not a finite ring. The nilpotents and the zero divisors and the integers is just only zero. Right? The units in the integers are only plus and minus one. Those are the only integers that have an inverse that's still an integer, right? Most of the integers are what's left over. Things like 2 and 3 and -7. And those things are neither zero divisors nor are they units. Right? Because 2, for example, is not a unit because 1/2 is not an integer. And it's not a zero divisor because you can't multiply it by a non-zero thing and get 0. Right? So, and that's in an infinite ring, you get these kind of elements like that are sometimes called regular elements. Okay. Other questions? Yes. Oh, well, yeah, so solvability. Solvability is, in theory, easy to tell because so you start with subgroup G. And let you want to be commutative. Now remember, this isn't just commutators. This is the group generated by commutators. Certainly, this thing is contained in Q because all commutators, remember, the commutator, so we're all on the same page. It's this animal. So every one of these commutators is in G, so it's just a subgroup of G generated by this. And this may be small. You take G2, you take what you've got here, G1, and you look at its commutator set. So you start with G. You go to this commutator subgroup, now you take its commutator subgroup. And then let G3 be the commutator subgroup of it. And so this gives a descending chain of groups, right? Every time you basically repeat this process over and over and over. Twice a table or something. Just keep going. G is solvable if G in the identity. So if in a finite number of steps, get all the way down to the identity group, then that's what it means to be solvable. Right? So for example, if you have an abelian group, it is solvable in the first step. Right? Because if G is abelian, then every commutator is the identity. And so what you're looking at in that first step is the subgroup generated by the identity, which is 1. So if you start with an abelian group, you get to the commutator in the first step. Right? Yes.
So for G of n, do we want that to equal the commutator subgroup of G to the n minus 1, and for that to equal the identity?
Well, you just repeat this process.
Yeah,
And if you ever get, if any of these outputs ever is the identity, then the group is solved. That's the definition of the group is solved. So for example, if you look at if G is S3, and G1 is S3, S3. Not there, so anybody know which one. Now, where that comes from, I'll show you a quick way to do this. I don't want to sit here and compute all the commentators. That is frankly a good pain in my butt that I don't want to deal with, right? There's a shorter way that I figured this out. But now that I know this, this is an abelian group, so every commutator is the identity. So S3 is solved. It takes 2 steps. And I can build groups that take as many steps as you want. 10 steps to solvability. Now, yes.
so when we're proving a solvability problem, what are the assumptions we can make? Like, what's like a sketch of proving a solvability problem?
I don't know what a solvability problem is. Like
Like
I mean,
if
I
you
can think
give us a solve problem like that. Like, what assumption should we start with?
well, see, I don't know what I've asked to prove. All I've told you is this is what it means to be solved. Right? And so, I mean, I can show you how I got Z3 here. This is true for any group. The commutator circle is normal. We actually proved this in homomorphisms. What are the normal subgroups of S3? They are S3, the identity, and the subgroup E, 1, 2, 3, 1, 3, 2. Of course, you're aware of this group. It has to be normal because it's index 2. Right? It's not 3. Y'all remember that any subgroup index 2 is normal. Right? I'm going to call this N. N is isomorphic to Z3. Also, the commutator is smallest subgroup G such that G mod commutator is abelian. This is something else to prove. I can't remember if this was in classroom in the homework, but it's some point. So this is, I've got 3 normal subgroups, that's 3, right? S3 mod S3 is the identity. Is that abelian? Yes. So the commutator subgroup could be S3. Right? Because the quotient's abelian. S3 mod the identity is S3. Is S3 abelian? No, it's not. S3 is not abelian. So E cannot be the commutator subgroup. Because the quotient is not abelian. What about this? This is isomorphic to Z2. So abelian. right? Because the quotient S3 mod n has two elements in it. There's only one group of order two, and it's abelian. So S3 mod n is C2. That means my commutator subgroup can only be S3 or n, but the commutator is the smallest group, such that when you mod out, you get an abelian group. So it has to be n. And so that's why I knew that was. So that's another big. Of course, again, what you can do is you can try to figure out what every commutator is in S3, but that's a complicated process, right? Because you've got two choices for X and Y, there's six. Well, right. So you choose X, choose Y, there's 6 things to choose from. It's a little bit obvious. Okay, any questions on how it got into that? Okay, other questions? Yes.
I fall
Mhm.
into 5C.
5C. Okay. Yeah. Okay, this is problem 5 on the exam in the fall. So it says, let R and T be commutative groups of identity. And P from R to T of ring homomorphisms. And F of X is polynomial integer functions. ANX. We're also going to assume here that the one R, that is, phi takes the identity of R, the multiplicative identity of R, or multiplicative identity. Okay, number one. First question is part A. Show that if M is an integer and N is a natural number and R is an R, then phi MRN is equal to M times phi R to the N. Okay, show this works. Okay. I'm going to do something probably more careful than I would expect that you to have done on the exam. Notice that if let me first point out that the business zero this works, because this is field zero and this is zero. Everybody agree with that? And of course, field zero has to be zero. Everybody agrees? If m is bigger than zero, then b m r n is b r n plus r n plus r n n times. Right, agree? And this is a homomorphism. So this is b r n plus b r n plus b r n times. Which is m b r n, right? Which is m b r. And this last step again is the fact that this homomorphism on R. So it's what do you suppose happens if m is negative? If m is less than zero, it's very simple. Then phi um, if m is negative, I'll pull minus sign out in front. Because remember, this is an abelian group homomorphism, so I can pull the minus out in front. It's like pulling out the inverse, right? And then now that the absolute value of m is positive, just repeat what we did before we put that together. So is everybody okay with that? Okay, so we've got that. Now number B, suppose that there is an existing element R such that f of R is zero. Show that f of phi of R is zero. Okay, so and here f of x is this polynomial function. This means a0 plus a1r plus a2r squared plus an rn is equal to 0. Correct. Now apply phi to this. Right? And I don't know much, but I know the phi of 0 is 0. And this is phi of a0 plus phi of a1r plus phi of a2r squared plus phi of an 0. Right? And now use the previous results to show did I do? Well, I use this in multiple ways. I pulled the A0 out of this, using that for in the case when R equals 1 there. And then I just use this formula repeated. And 1R is the identity of T. So I can write this as A0 softly, A1 phi of R plus AN D of R and T. So in other words, F of phi of R. And now to the question at hand is asked. So what this says is, if there is a homomorphism, so let me explain what we've done in part A and B. If there's a homomorphism between from R T, and R is a root of f of x, some polynomial with integer coefficients, then B of R is a root of f of x in T. That's what we've shown. Right? Everybody with me so far? And here's how this applies. It says use the homomorphism. And here's the way the homomorphism from Z to Z7, we've worked on this kind of thing before, is you just take whatever the integer is for your input, call it K, and reduce that mod 7. Right? So 1 will go to 1 bar, right, mod 7. And 8 will go to 1 bar mod 7. And 14 will go to 0 bar mod 7. And 26 will go to 5 mod 7, and so show polynomial. Or if I have x cubed minus 70x squared minus 2100 x minus 5 as this actually shows that this is another powerful problem, because how do you know that polynomial doesn't have any integer solutions? Do you want to try? Do you want to freaking try forever? Right? Because there's lots of things you can try. There's infinitely many integers, and how are you ever sure that oh wait a minute. I think I've seen here. I'm sorry, I think that's supposed to be equals 5. This appears to be a typo. I didn't can you all see the exam? What does it say? The polynomial x cubed minus 70x squared. Did I read that right? Minus 2100x minus 5?
Yeah.
Has no integer solutions. Of course it doesn't. That doesn't make any sense. I guess what it meant. I wonder if that's a typo. Let's see. Yeah, has no integers. I mean, nobody wants to check this, right? Check that zero solution is terrible. Well, suppose it does. Instance. Well, that would be that R cubed minus 70 R squared minus 2100 R minus 5 0 if there is a integer root. If I agree with it? But so this means that phi of R is a root of so if I look, so whatever this root is, maybe it's 26, phi of R, which mod 7 would be, I guess, 5, should be a root of this, mod 7. And that is much easier to check because there's only finite and many things. Also, let me point out, it gets easier because if you have x cubed minus 70 x squared minus 2100 x minus 5, 0 in Z7, you can simplify this quite dramatically. Anybody see why you can simplify this? Remember, you're in Z7. What can you say about this term right here? It's 0, right? Because this is multiple 7. This is also 0. So you would have to have a solution. And I can check the cases. That's, in fact, I'll check. Mod 7, 2 cubed is 8, which is 1 mod 7. 3 cubed is 27, which is 6 mod 7. I'm gonna do these faster. How did I do that so fast? Everybody agree that 3 cubes is 6? 3 is the same, or 4 is the same thing as -3. So 3 cubes to 6, 4 cubes to -6, which is 1. This cubes to the negative this, which is 6. And well, this is -1 itself, so it should cube -1, which is 6. Is there a 5 here? There's no 5. This equation has a solution mod 7. So there's no integer that satisfies the messy polynomial. You're never going to triumph in many cases until you're blue in the face, it's not going to work for you. But here, use this homomorphism to reduce it down to something that only has to be checked a finite number. Only a finite number of things you check, verify it. Yes.
I don't know if it's input up, but was C7 like part of the question, or did you pick the homomorphism?
No. So Z7 is part of the question.
Okay.
Okay, other questions?
Up to what point in the textbook is the example?
Let's say the definition. prime and max one equals and radicals, so it's part of it, like today. Right, whatever it was that I ended on. We'll just say, as far as the definitions, they'll end at prime, max, and radical items. That'll be the upper limit to what I might do. I don't know where that is in the address.
Yeah, it's like 9.3
But I'm not gonna play with that more fun. So. So we look at the theologist. My brother was good friends, I should say that's about well studies. Anything else, Sean? Oh, by the door here, you just ring my phone.
Okay.
Yeah. So they're everything answered.
Like kind of, if you just like how much you need for the answer and you get a bunch of problems, then like I think I know like
Right,
what
okay.
to put with that, but it's much
Well,
less content.
You're gonna be less. I'm gonna be less manual to write down on exams than I expected writers to be.
And I appreciate that.
Yeah, so, well, and actually, I don't wanna throw the grader in the bus because I make him do that.
Yeah.
Because I want him beating on you. I would rather the exam say, okay, that was easier. That's much better than saying the homework's like a bunch of softballs and the exam rips you new.
It's like every time I look at the average mean and the mean is like a 65 on the homework, I'm like, this is pathetic. I'll get like a two, number 6.
Homework 10.
Yeah, that's the extra problem that you said we didn't practice events.
Oh, I would rather, I think, let somebody work it if they want to turn it in, but let me remind myself. Oh, I know what it was. It was all that business about,
It was a ring with ABA equals A.
yeah, I remember that. I'd have to get it up here to make sure that I get all the details right.
Mark your rank property that for all non-zero A and R versus the R's that you can change, right? Yeah, just for it.
I would rather not do this recorded because there may be some people that want to turn it into fun or something like that. So if you want to, and the other questions, if you don't want to do it for fun, and the other questions are done, turn off recording. Okay, any other questions? You may turn off the recording and work through that problem.
Oh, sorry, I do have a question.
Okay, yeah.
You do, number 2 from 2020.
The R be a ring, I, an ideal, or an S subring. So I intersect S is an ideal S. So, um, you'll, S Not separate. Show I intersect S and S. And well, number one, I intersect S is a subgroup S. We know that from just the fact that I is a group, S is a group, and their intersection has to be a group. This is what we did from like intersections and subgroups or subgroups. Is that okay? Yes.
I just have a question before you continue. So, since we're trying to show that it's the intersection of these two, would the right approach here be to show like that if I is an ideal and S is an ideal, then their intersection I and S is an ideal?
No, because S may not be an ideal at all. I is an ideal in R, S is just an ordinary subring. Right? And what you're trying to do is show, so you've got R as a ring, and you've got S as a ring inside. And you've got this ideal I and R. This thing is vacuum cleaner, it sucks everything in. You want to show the overlap between this vacuum cleaner inside the subring S. That's what's happening. So I is vacuum cleaner. S is just an ordinary subring. I is a subring on steroids. It's vacuum cleaner. It sucks everything in from R. You want to show that the overlap I intersect S is actually an ideal inside sub S.
So, is like the reasoning that it's an ideal is because it's contained in I? Like the intersection, so it like inherits that like back to
Well,
the
let's see.
property.
Let's see, there's two things you have to do to show it's certainly I intersect S is contained in S by definition. And it has to be a subgroup of S because it is an intersection of two groups. An ideal and a subring are both groups. Their intersection is group and is contained in S. So that's the first step, is that I intersect S is in fact a subgroup of S. And now we're going to show it's a vacuum. So two, let X be an I intersect S and S and S. Well, notice that SX is in I because S is in R and I is an ideal. So this is an element of R, and actually not just that, XS. In both directions, S is sucked in by X and I because it's an element, right? Also, XS and XS are in S because S is in S and X. And that's because S is a subring. So it's closed under multiplication. Therefore, both XS and SX are in I and S. So I intersect S in S is it's a subgroup and it's such stuff in from both sides. Any questions? Yes.
I'm just kind of confused. When you're showing that something is an ideal, don't you need to have like a containment somewhere in like your work, like you know how like
Yeah.
the formula is.
And I intersect S is contained in S.
Uh-huh.
And that, so here the ring is S. I intersect S is contained in S, because anything intersect S is contained in S. Right? So I intersect S is contained in S. It's a subgroup. And it's such stuff in from both sides, so it's not.
So if X is like the element from the ideal and then S is the element from the ring. So what we're showing is that XS is contained in.
Yes, we're showing that X times S. We want to show that any X here, if you hit it by any S in the ring, on either side, it's still an I intersect S. First step, we show that it's in I. And that's because I is an ideal ball. Next step, we show it's an S, and that's because S is a subring, and both X and S are in S. So their product is an S. And so therefore, XS and SX are both in U. So that's it's such stuff in from both sides. I intersect S is contained in S. It's a subgroup. And when you take anything there and anything in S and you multiply in either order, it's still in there. So it's not.
So you could say S times I intersect S is still contained in I intersect S. And then.
Oh, yeah. So are
Like,
you
that's
confused
what-
about this?
Yeah.
Right. That's exactly what I'm showing element wise. What this means is for every I and every R and R times I is still in it. Okay? So I'm just doing it with elements, but it's the same thing.
So the XS in I shows that RI is still an I, and then the SX shows that IR is still an I.
Yeah, that's right.
Okay.
Yeah, I guess XS is the IR and SX is our I.
And since it's the intersection of I and S, that's why we can show that SX is in I, and then SX is also in S. For it to be in I and S.
That's
Okay.
Yes.
Could you do a really quick elementary divisor problem?
We did a bunch before it came to a bunch.
Oh, that's right.
Yeah, I can. So,
Do you have one in mind? I can do. You want to do
literally any. It doesn't have to be like a big number.
Okay, so I want to do elementary divisor, and invariant factor decomposition. So I'm going to do this. See how I got all this?
Yeah.
So I took each of these and broke them up into compounds. And in a certain sense, this is already in the elementary divisor decomposition, but it's not very pretty. And it's not very organized, and it doesn't really help my next step. So I'm going to dramatically let out next step for the elementary divisor decomposition. Let's see. Start with twos. Oh, I got 4. 4 make 4. 8. Okay, so that takes care of that. The next problem I see is 3. One right here, so I see 3. See 3. Let's step through Z3. This size problem is 5, but 1, 5, 2, 5, 3, 5. Better move C7. This is, of course, a little bit more organized. 2, 4, 6, 8, 10, 12. 4.
Could we leave it like that on the exam?
I think we'll do it. I just rewrite it. And I'll show you why. You can, but you probably need to tell me. This really is, tell me why you know. When I see that, I know it's an elementary, but it's a build a problem. Group together. So the invariant factor I can get by doing kind of the following algorithm. Yeah, there should be 4 invariant factors. Just do the biggest 8, 3, 5, 7. So that's 1. So that's 840. That's that. Great. The next one, I pull off next highest. 4, 3, 5, 7. I mean, nothing really changed except for just out the first one. This was. The next one. 4, 3, 5. So let's see, 6. And after that, all I've got left is this lone Z4. And so they're your invariant factors from small to big. They're 4, 60, 40. Yeah, and these are very, if you do this kind of computational combinatorial algebra, things like this. If I ask you for example, you'd probably get pretty angry. If I ask you to find zero-divisors in here, then this might be the easiest decomposition. There's an enormous number. Let's not do that right now. But the different decomposition is sort of differently useful. It depends on what folks are going to do with your version. Yes.
So when we do, like, if we have to do a decomposition problem for all, like, do we need to say justify that this is invariant factor and say the cycles and then M1 divides M2 divides up to MK.
If I just ask you for the decomposition, you should be able to tell you what the invariant factors are if I ask for them. But if I just say, give me the invariant factor decomposition, I mean, the more you can say, the better, probably. But I mean, if we've been doing the test, if I had literally gotten that problem, I would have gone through there. I would have made clear which one was elementary divisor, which one was the invariant factor, and I would have moved on with my mind. And if I wanted to polish it later, I'd make sure I was done with my other stuff.
So the invariant factors here are 8.
That's correct. That's correct. The elementary divisors are the prime powers involved. The elementary divisors are 8, 4, 4, 4, 333, 555, 77. Other questions? Questions?
When you're finding all abelian groups of a certain order, that's when you can break them down into ones, like into Z's that are not relatively prime to each other.
Will that not be in?
Like in homework 9, question 1, when it says find up to isomorphism all abelian groups of order 15,000.
It's 15,000.
Yeah.
Okay.
Then you can break it down into non-relatively prime C's. But if you're
Well,
doing
so here's, yeah, so what I would do that. So you're trying to find all groups for 15,000. Abelian. Not its right. Let's say.
yeah, there's a lot of them. I just want to make sure you can break them down into non-relatively prime C's.
Right, so. I would do this just keying off prime powers. Order. Q. Well, we have C8, we have C4, right, some C2, and C2, 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 and that's it. Right, it's basically, this is 2 cubes, partitions of 3. 3 can be written as 3, 2 plus 1, because that's the square power, the first power, and 1 plus 1 plus 1. Groups of order 3, C3, and that's it. Groups of order 5 to the 4, C, whatever 5 and 4 is, which is, I guess, 6.5. And have C, that's the 4th power, and 3rd power. Have 2 squares. It's 4 1 equals 2. 1 4. And 1, 2, 3, 4, 5. So basically what you're doing is you've got 3 things to pick from here, your choice here, you don't have 5 things here. So there's 15 ways to go. Yes.
So like the answer of that question would just be like the elementary divisor decomposition, like written out like that.
Actually, I think in the homework, I didn't care what you did. I think I gave the grader a list of the elementary divisor decomposition and the invariant factor decomposition. I'd stick to one or the other, right? I wouldn't half of them in invariant factor and half of them in, because that's gonna make the grader angry, because then they gotta go through and check that they're really different, right? So. Okay. Other questions? Yeah. Williams? You want to try to, when we talk recording, try the other problem?
Unless somebody else has,
Is that
unless somebody else
unless somebody else would?
has a question. One.